All right. In this video, I'm going to go through the procedure sections of Lab 8. There are 4 of them. One of them is coded in a separate web-assigned question, simply because there wasn't space in the first question. So keep this in mind when doing the procedure sections. Some students forget to do procedure section C, which is at the very end of the first question, or procedure section D, which is part of its own second question. Okay, let's take a look at procedure section A. So in this lab, we're going to simulate the expansion of space with a rubber band. So in this section, you're going to prepare your rubber band. You can see we have dots on the rubber band that represent galaxies, but the galaxies don't move through space. Rather, space will expand, pulling the galaxies apart from one another. So to prepare your little one-dimensional rubber band universe, take your rubber band, cut it with the scissors, and place it down next to your ruler along the centimeter scale. Using your marker, you're going to put dots at 3, 6, 9, 12, and 15 centimeters. That's galaxies 1, 2, 3, 4, and 5. And place those dots very carefully, because that will affect your measurements and the auto grading for the rest of the lab. Then let's try it out. Put your push pins through galaxies 1 and 5 and push them into the foam board or whatever foam board substitute that you're using. Now the push pins may be longer than the foam board is thick, in which case you may have to pull the foam board over the edge of the table so the pin can go all the way through. Now here you see it in the resting position. Next, unpin galaxy 5 and stretch it all the way out to 27 centimeters and pin it again, just to make sure that it will hold. Now, when you put the pins in, be sure to put them in at an opposing angle. This will help prevent them from becoming dislodged and flinging across the room. And be sure to push them all the way in as well. Okay. Once you have all that ready, let's head into procedure section B. And in this section, we're going to show that Hubble's law is a natural consequence of the expansion of space. And we'll spend a fair bit of time on this section in this video, so you see how it works, how you can measure Hubble's law from your rubber band universe. After which, you'll repeat this procedure 3 more times in the following sections, measuring different things and under different conditions. So in this section, we're going to simulate a universe that's expanding at a constant rate. And that rate will be measured by the distance between galaxy 1 and galaxy 5. In this particular example, this distance is going to increase 3 centimeters every minute. Now in this lab, you'll have godlike powers. You'll be able to halt time, carry out your measurements, and then jump to the next time and carry out your measurements. So let's take a look at this table. In this table, we have times 0 through 9 minutes, and the distance between galaxy 1 and galaxy 5 is increasing from 0 to 27 centimeters. Now at time 0, 1, 2, and 3, you can't carry out any measurements because the rubber band would actually have to shrink, and rubber bands don't do that. So these boxes are grayed out. But beginning at minute 4, the distance between galaxy 1 and galaxy 5 is 12 centimeters, and that's the resting size of the rubber band. And so using your ruler, you'll measure the distance between galaxy 1 and galaxy 2 and put that here, between galaxy 1 and galaxy 3, put that here, and between galaxy 1 and galaxy 4 and put that here. You don't have to measure the distance between galaxy 1 and galaxy 5, because that's what sets the length of the rubber band, and you set that to 12 centimeters. Then you'll hop to the next time, 5 minutes after your rubber band universe's Big Bang, and the distance between galaxy 1 and galaxy 5 is then 3 centimeters bigger, 15 centimeters. So using your push pins, fix the size of the rubber band to that, and again, measure the distance between galaxy 1 and 2, galaxy 1 and 3, galaxy 1 and 4, and put those here. Then you repeat for time equals 6, 7, 8, and 9 minutes, where 9 minutes corresponds to now in this particular example. And once you've done that, we'll come back and use your measurements in just a second. But first, let's just confirm that this universe is expanding at a constant rate. And the way we're going to do that is we're going to take these times and these distances between galaxies 1 and 5, the distance that you set the rubber band to, and plot them. So let's go to the graphing website, and we'll, for this, use just the simple curve option. And I have those values here, and I'll put them in. Let's label our axes. On the x-axis, we have time measured in minutes. The y-axis, we have distance measured in centimeters. And the title can be something like distance between galaxy 1 and galaxy 5 versus time. And looking at this, this indeed appears to be linear, so a constant rate of expansion. This is a universe that's expanding at a constant rate. So you'll save that PNG and upload that here. And it asks you a question: is this universe expanding at a constant rate? And if you confirm that, you'll mark yes. So next, we're going to measure Hubble's law as it appears to galaxy 1 in this constantly expanding rubber band universe. Now remember, Hubble's law is a plot of two things: distance between galaxy 1 and the other galaxies on the x-axis, and the measured redshift of these other galaxies on the y-axis. So distances and redshifts. And we can get both of these quantities from the measurements you've made. Let's start with distance. Now it's a little tricky because what distance are we talking about? In an expanding universe, there are different distances to consider. For example, there's the distance between the galaxies when the distant galaxy emitted the light that we're just now receiving, and there's the distance between the galaxies now. In an expanding universe, these two are not the same. The first one will be a smaller distance, and the distance between the galaxies now will be a larger distance. And we can read both of these off of this table. The yellow boxes correspond to how far away these galaxies were from galaxy 1 when they emitted the light the galaxy 1 is just now receiving. At that point in time, they were closer together. And this bottom row shows how far apart the galaxies are now. And that's, of course, greater. So we call these D then for the yellow boxes and D now for the bottom row. And what you're going to do is take these values and copy them into this table here. The D then values from the yellow boxes put in the first column, the D now values from the bottom row put in the second column. Now, how far the light actually travels will be something between those two limits. And the equation for calculating that can be somewhat tricky, but in this lab, it's good enough to simply average the two values. You see that here, d then plus d now divided by 2. And that gives us something we call coordinate distance. That's the distance you would get if you had some giant ruler that you could stretch out through the expanse of space and measure the path that the light took. Now, of course, astronomers don't have that ability, but we can measure distances across space. We just do it using standard candles, such as Cepheid variable stars or type 1a supernovae. And when we measure distances in this way, we get a somewhat different value, a distance that we call a luminosity distance, and it's somewhat greater than coordinate distance for the following reason. The standard candle is emitting light, and the light is coming to us. Think of a train of light coming to us through space. But as it's coming to us, the universe is expanding, stretching out this train of light. So when we eventually receive it, we receive it at a slower pace. That will make the object appear somewhat fainter, and consequently, we will infer that it's somewhat farther away. And luminosity distance is what we want to plot because that's what the astronomers plot. Now you can calculate luminosity distances from your coordinate distance and your d now and d then pretty simply. Luminosity distance is just the coordinate distance times this correction factor. And the correction factor is just d now over d then. So coming back up to this table, in the third column, we're going to put the luminosity distance. And remember, to get that, first you average d then and d now, and then you multiply it by the ratio of d now over d then. So calculate those values, put them in here, put a sample calculation here. Okay, that's half of Hubble's law. The second half is the redshift. Now let's remind ourselves, what is redshift? Redshift is change in wavelength divided by the emitted wavelength. So in other words, the wavelength now minus the wavelength when it was emitted, so the wavelength then, divided by the wavelength then. And as we talked about in the background sections, the wavelength of light just expands with the universe. If the universe doubles in size, the wavelength of the light doubles in size. In other words, wavelength is proportional to these distances that we're talking about. Wavelength then is proportional to distance then. Wavelength now is proportional to distance now, where proportional means equals to some constant times the distance. So let's substitute these into this equation. The redshift is then the constant times d now minus the constant times d then, whole thing divided by the constant times d then. And this simplifies. The constants cancel out. We don't need to know what this constant is. And redshift is simply d now minus d then over d then. That's pretty straightforward to calculate. You have your d nows here, your d thens here. You can calculate the cosmological redshift and put that here. And we'll put an example calculation here. So now we have our luminosity distances, 5 of them if we include the 0 point, and we have our cosmological redshifts. So to get Hubble's law from this rubber band universe, we just have to plot one versus the other. So we go back to the graphing website, and we'll again use the simple curve option, clear out the fake data, and you'll enter, starting with the 0, 0 point, you'll enter 4 more sets of values. On the x-axis, we have luminosity distance, measured in centimeters. The y-axis, we have the redshift, which is dimensionless. The title can be simply redshift versus luminosity distance. And you'll plot it up and we'll see what it looks like. You can save it as a PNG. Then upload it to WebAssign here. And then it asks you a question. Hubble's law states that the farther a galaxy is away from us, the faster it appears to be moving away from us. Have you replicated Hubble's law? If so, answer yes here. Okay, so what we have done is we've determined Hubble's law as measured from galaxy 1. Now suppose we are in galaxy 1. As we've already learned, that means all the galaxies appear to be moving away from us, and you could come to the mistaken conclusion that you are at the center of all things. If everything is moving away from you, maybe you're at the center. So in procedure section C, we're going to repeat this experiment, but we're going to make all of our measurements from the vantage point of galaxy 2. So here we have the same table, the same times, the same distances between galaxy 1 and 5, but here you make the measurements with respect to galaxy 2. This is the distance between 1 and 2. This is the distance between 3 and 2, between 4 and 2, and between 5 and 2. And note, these should all be positive values, even on this side. There's no negative direction in space. Now, your D-thens are again in the yellow boxes. Your D-nows are again on the bottom row. So you'll copy those into this second table. The D-thens go here, the D-nows go here, and then using the same equations, you will calculate luminosity distances in this column and cosmological redshifts in this column. And then you're going to plot up Hubble's law as measured from galaxy 2. And in this plot, you're also going to overplot Hubble's law from the previous section as measured from galaxy 1. So there's a tutorial here showing you how to plot two curves with different x values at the same time. And then you'll go to the graphing website, and this will be the option called dual. And you'll plot, again, both Hubble's law from galaxy 2 and Hubble's law from galaxy 1 and see if they're the same or different. You'll save that, upload it here, and then you have two questions to answer. The first is, do observers in galaxy 2 have as much right to say that they're at the center of the expansion as observers in galaxy 1? And then the next question is, can anyone claim to be at a unique center of the expansion and hence at the center of the universe? You'll be able to answer these based upon your figure. Lastly, we have procedure section D, where we're going to try to figure out whether we live in a decelerating, constantly expanding, or accelerating universe. So we're going to repeat this 2 more times, once in a decelerating universe and once in an accelerating universe. And we'll make all of our measurements with respect to galaxy 1. Now, the decelerating universe is what everyone expected. Yes, we have this initial expansion. We don't know why, what caused it, but space is stretching, pulling everything apart from everything else. But we thought that this expansion would slow with time because of the mutual gravitational attraction of all the matter and energy in the universe. It wants to pull itself back together, which would fight against the expansion. Now, if we live in a decelerating universe, this affects Hubble's law at great distances at high redshifts. So here we have a decelerating universe. We have time in this column, the distance between galaxy 1 and 5 in this column, and then you'll make your measurements. just as before. So the first thing you're going to do is go to the graphing website, and you're going to plot how the distance between galaxy 1 and galaxy 5 is changing with time. So these data on the y-axis, these data on the x-axis, just as you did before. And you're doing this just to confirm that this is indeed a decelerating universe. In fact, you'll overplot these data from the previous section where the universe was expanding at a constant rate, just so you can compare and contrast the two and see more easily that this is indeed a decelerating universe. You'll save that figure and upload it here. Then it asks you the question, is this universe decelerating as it expands? Yes or no? And then you're going to take your measurements and move the d-thens and d-nows down to this table, calculate luminosity distances and cosmological redshifts, and then go back to the graphing website and graph Hubble's law in a decelerating universe. And again, you're going to overplot Hubble's law in a constantly expanding universe from before, just so you can compare and contrast them. Once you've done that, you'll save it, upload it to WebAssign here. Then it asks you, how does Hubble's law change in a decelerating universe? It curves down at large distances, it does not change at large distances, or it curves up at large distances. Lastly, we're going to repeat the experiment with an accelerating universe. That's what we have in this table. You'll begin by making your measurements, but then you'll make a dual plot of how the distance between galaxy 1 and galaxy 5 is changing with time. And again, you'll overplot this for a constantly expanding universe, so you can compare and contrast and confirm that we are now looking at an accelerating universe. And you'll save that figure and upload it here. And it asks you, is this universe accelerating as it expands? And then you'll take your d-thens and d-nows and move them down to this table and calculate the luminosity distances and the cosmological redshifts, and go back to the graphing website and plot Hubble's law in an accelerating universe. And again, you'll overplot Hubble's law in a constantly expanding universe for comparison. You'll save that, upload it to WebAssign here, and it asks you how Hubble's law changes in an accelerating universe. Again, it curves down at large distances, it does not change at large distances, or it curves up at large distances. So, as I've already said, Hubble's law is different at large distances in a decelerating universe and an accelerating universe, and we can use that and measurements to determine what kind of universe we live in. So over the past couple decades, there have been a lot of measurements of type 1a supernovae, measuring both their distances and their redshifts. And initially, it does look to be fairly straight, but then you can see the data collect on the downward side. Here we have the curve corresponding to a constant rate of expansion. These other curves, one of them corresponds to a decelerating universe and one corresponds to an accelerating universe. And so you'll be able to use these type 1a supernovae data to determine what kind of universe we live in. You'll answer that in this question here. Now, the result surprised many scientists, and we don't yet have an explanation for it. We call the explanation dark energy, but we really have no idea what dark energy is. It is that thing that explains these data, basically. Nonetheless, I want you to look it up and discuss dark energy, what little we do know about it. And then in this last question, discuss your significant sources of error. Okay, that's it.